In this video, we're going to be looking at electricity, and we're going to be talking about what we call static electricity and current electricity. Now, if you want to talk about electricity and you want to start at the beginning, you really have to talk about Benjamin Franklin, who was, famous in the United States as being one of the founding fathers of our country, but he was also famous around the world for being an incredible scientist. And a lot of the times, Benjamin Franklin doesn't get the credit he deserves because he was an absolutely remarkable scientist who made contributions to many different fields of science. He was also an incredible inventor. He invented many different things which made the lives of people better. But among many other things in his life, he was famous as a publisher too. He published newspapers and books, and he became very wealthy through some of his publications. He also worked as a politician. As I said, he was one of the founding fathers of the country. He was involved in the writing of the American Declaration of Independence. Thomas Jefferson wrote it, but Benjamin Franklin was sort of the editor. And of course, he was a famous statesman and diplomat. It's actually the incredible work done by Benjamin Franklin that was able to, as a diplomat, that was able to secure the financial and military support of the French. And really, that was what turned the tide and enabled the American colonists to defeat Great Britain. And so, maybe as much as anyone else, he's responsible for the United States being successful in its independence effort. Now, here's a painting of one of Franklin's most famous experiments, and you might have learned about this experiment in grade school, though you probably didn't really learn what the experiment was attempting to show. He's got a kite, and he's flying it high into the clouds of a thunderstorm, and he has a key at the other end. And people say that he discovered electricity. Well, actually what he was doing was, have you ever scuffed your shoes across a carpet and made a little spark and when you tried to touch a doorknob? What you're doing when that happens is you're actually making a little bitty lightning bolt. And Franklin did many experiments with electricity, and he was able to make these little mini lightning bolts sort of on demand through some of the equipment that he built. And the question he wanted to know was, is the lightning in the sky the same thing, just on a bigger scale? And so what he did was he flew this kite up into the cloud, which was electrified, and the current would be conducted down the string to the key, and the electricity could be released by the sharp edges of the key, and he could show that the kinds of things that would happen with the key are the same things that would happen with the electricity generated in his lab. So basically, what Benjamin Franklin, with this experiment, was able to prove was that lightning was just a phenomenon, a natural phenomenon of electricity. It wasn't Zeus throwing thunderbolts to punish evildoers or anything like that. It wasn't God's punishment. It was just a phenomenon of nature. And it was something that could be understood and even controlled. One of the things that Benjamin Franklin invented was the lightning rod. And what he recognized from his work in electricity in his lab is that if you have a metal and the metal has a sharp edge, the electricity will actually be attracted to the sharp edge. And so what you can do is you can take a metal pole and grind it to a point so it has a sharp edge, and put it on a building. And then you can take a conducting wire and bury it in the ground. And so the sharp edge of the metal conductor is going to attract the lightning strike, and then the conducting wire will carry the lightning into the ground. Now, in Franklin's day, buildings were made out of wood mostly. So your barn, your house, if lightning struck them, they could burn it to the ground and kill your livestock or even kill your family. Lightning was something that was very scary. But by understanding that lightning was an electrical phenomenon, he was able to make a very, very simple invention that saved people's lives, saved people's homes, by controlling nature through understanding nature. And that's really one of the great things about science. All the modern conveniences we have in our world today are here because of the work done by scientists like Benjamin Franklin. Now, there's an interesting fact about nature that certain materials, if you rub them together, they become electrically charged. One of the two materials will become positive and the other one will become negative. Now, before Franklin, people thought that the process of rubbing was somehow creating charge. Franklin recognized that this was not the case. Through his many experiments, he recognized that there were basically two types of charge. Now, what he imagined was that by rubbing these objects together, you were transferring some kind of fluid. And so the objects, you've got two objects, and these objects are not charged. There's no kind of excess charge on them. But when you rub them together, what Franklin imagined was that there was some kind of fluid that would transfer from one object to the other object. And that would make this object negative because it gained electrical fluid, and the object that lost the electrical fluid now has less negativeness, and so it becomes positive. And so this is how Franklin imagined the process of charging. And he wasn't that far off, because we know that atoms today have two kinds of charges built into them, positive and negative charges. The protons in the nucleus of the atom are positive, and the electrons around the atom are negative. And what happens when you rub certain materials together is that the electrons can transfer from one material to the other. And the electrons that get transferred make that object negative, and the other object has lost electrons, so it's left with an excess of positive charge. A neutral atom has as many electrons as it has protons, so the charge is balanced. But once you start moving electrons from one atom to another, you create an imbalance of charge. One object will be positive because it's lost electrons, and the other object will be negative because it's gained electrons. Franklin is actually the one who came up with the names positive and negative to describe the different kinds of charge. So that kind of naming goes way back to Franklin's day. Another thing that Benjamin Franklin recognized was a rule that you probably learned in grade school. Like charges repel one another. So if I have two sets of positive charges or two sets of negative charges, those are going to repel one another. But if I have a set of opposite charges, one group of positive and one group of negative, they're going to attract. And you can sort of see that sort of depicted here in this picture. If I have this rod that's suspended and it's charged, and I have another rod that's charged, if they have the same kind of charge, the two rods are going to repel one another, and this guy will spin away. But if they have opposite kinds of charge, they'll attract, and this guy will spin towards this guy. So here on this slide, I've summarized that very important rule. So I'm looking here, these two yellow charges are positive. We know like charges are going to repel. These two purple charges here are negative. Again, it's the same kind of charge. Both are negative. They're going to repel. So if they have the same kind of charge, they're going to repel. But if you have a positive and a negative, we know that the electrical force is going to be attractive. The two charges are going to attract one another. And that is the fundamental rule of electric charges. Now, I already reminded you of this in another slide, that the atoms that make up the matter that exists in our world, they have three different types of particles. They have protons in the nucleus, which are positive. They also, notice there's a little plus here and a little plus there denoting these two protons. They're positively charged. There are also in many atoms neutrons, which are neutrally charged particles. They are not positive or negative. And so we know that the nucleus of an atom is made up of both positive protons and uncharged neutrons. And then flitting about outside them are these tiny little negatively charged electrons. Also, you should maybe remember from your grade school classes that the amount of charge on the electron equals the amount of the charge on a proton. So if this guy has two protons and two electrons, there's two positive charges and two equal negative charges. So the whole atom has no net charge. We say it's electrically neutral. And over here on the right, we can see the same sort of effect. I've got these two charged particles that are dangling from strings. If they're positive, they're going to repel one another, but even if they were both negative, they would repel one another. The key thing, they both have the same kind of charge, so they're going to repel. Here, however, they have opposite charges, so you can see that the two charges are attracting one another. Now, this part of the slide over on the left has one of the figures from your textbook, and it asks an important question for you guys to understand how this is working. And so it says, when a rubber rod is rubbed with fur, electrons transfer from the fur to the rod. The rod's gained electrons, so the rod is then negatively charged. The question is the fur charged? By how much compared with the rod, and positively or negatively? So think about how the rod became negatively charged. Electrons flowed from the fur onto the rod. That means that this guy has lost electrons and this guy has gained electrons. Can you see that their charges have to be equal? Because if this guy sent over 50 electrons, it's now lacking 50 electrons. And so it's going to have a net 50 proton positive charge because there's no longer 50 electrons to balance those protons. And so the amount of charge is going to be the same, but it's going to be the opposite side. This is a principle called conservation of charge. We've already seen conservation of energy and conservation of momentum. The conservation of charge says that the total charge of a system is constant. Now charge can move from one body to another body, but if one body gains a charge, the other body has to lose the same amount of charge. The charge is conserved. Now, here's one of our checkpoint questions. It says, if you scuff electrons onto your shoes while walking across a rug, are you negatively or positively charged? The answer is you're negatively charged because you've gained electrons onto your body, or at least onto your clothing, and so you have an excess of negative charge. The other question, and you can see this figure here, why do you get a slight shock from the doorknob after scuffing across the carpet? What happens is you can gain so much excess charge that when you touch the doorknob, it actually flows to the doorknob and it makes a little bitty lightning bolt and you get zapped. The same thing happens with lightning in clouds. What happens inside of clouds is there's dust and ice crystals and they're rubbing together and they get charged up. And through different mechanisms, that charge gets separated and the charge builds up so much that it actually creates lightning that flows either from one cloud to another cloud or from a cloud to the ground. And that's what creates a lightning strike. It's just at a much larger scale because a cloud is much bigger than you are. It can hold a lot more charge than you can before it discharges. Now in this slide we have Coulomb's law. And Coulomb's law tells you the amount of the electric force. We know that like charges repel one another and opposite charges attract each other, but by how much do they attract or repel one another? Now, the formula for Coulomb's law says that F is equal to K Q1 Q2 over D squared. Now, the two different Q's, Q1 and Q2, these are the two charges. I've got two charges that are either attracting or repelling. The Q is the quantity of charge that you have. And the units for charge are something called coulombs. Just like the units for length are something called meters, and the units for force are something called newtons or pounds, depending on what kind of force you're talking about. Charges are measured in something called coulombs, and so more coulombs means more charge. Now, the D value here, that stands for distance. Specifically, it's the distance between the two charges. And then finally, we have this K value, which is typed out here, and it's equal to, you can see this is 9 billion, 9 with 3 zeros, 3 zeros, 3 zeros, newtons times meters squared divided by coulomb squared. That just makes all the units work out so that your force has an answer in a unit of newtons. Your force has an answer with a unit of newtons. And so it's worth noting that this number for K is a really, really big number. Now you might recognize this equation. It might look like something we've seen before. If you remember, the force of gravity looked very similar. It said the force of gravity between any two masses, which you multiply the masses together, you divide by the distance squared, and you multiply them by this constant big G. And if you remember, big G was a really tiny number. And so what this shows is that the electric force is way, way stronger than the gravitational force. In fact, there's a demonstration. When I teach this class as an in-person class rather than online, there's a demonstration I like to do where I rip up some little pieces of paper and I put them on the desk and I run a comb through my hair. By running the comb through my hair, I put some charge on the comb, just like rubbing the rod in our previous example. I'm putting charge. And if I hold it over the pieces of paper, the charges in the comb will actually attract the opposite charges in the paper, and the paper will leap off the table and stick to the comb. And so just by raking the comb through my hair a few times, I put this tiny little bit of charge on the comb, and the electric force between the charges in the paper and the comb are able to overcome the gravity of the entire planet Earth pulling down on those papers. So that sort of shows just how strong the electric force is compared to gravity. But other than the strength of the two forces, there's one other very important difference. Gravity is much, much weaker than the electric force, and gravity only works in one direction. It's always pulling or attractive. Two masses are always going to be gravitationally attracted, pulled towards one another. The electric force can be attractive, but it can also be repulsive. And that's actually a pretty important difference, that the electric force can both attract or repel depending on what kind of charges you have. Now, one of the first ways that people thought about atoms was they thought about satellites orbiting planets, like the moon orbiting the Earth. And so what they imagined was they had the proton was at the center of the nucleus, and the electrons were up above, and the electrons were sort of orbiting around the nucleus the way that a planet orbits around, the way that a satellite orbits around a planet. So this picture was actually really useful for understanding the structure of atoms. Like, for example, you can note in both cases, there's a lot of space between the electrons and the protons. It turns out that atoms are mostly empty space. You've got the charges in the middle and the electrons up above. There's a lot of empty space in between them. But this model's not quite right, because the electrons aren't orbiting in this nice regular way. What they're actually doing is jumping. You might even think about it as like teleporting. So the electron's over here, and then it teleports over here, and then it teleports over here, and then it teleports over there. And over time, it covers this whole circle, just randomly teleporting from different spots. But it's these jumping things that happen. And the fact that these electrons can jump like that will be important later on for those of you that take physical science too and get into some of the chemistry of how electrons behave. Now, this is a sort of another way that atoms are often depicted. And so imagine that, like, every time the electron teleported, it made an image on a piece of film that you were filming where the electron was. You can't actually film electrons. They're too small. We're just imagining that if you could film where the electron was, over time it's jumping all these different places. And so if every time the electron jumped somewhere, it left a mark where it had been, it would start to look kind of like this. And you can see it's kind of darker out towards the edges. There's a few times it's in close to the nucleus, but mostly it's towards the outer side. And that's the normal way that we think about the electron. And this, instead of thinking the electrons as orbiting, we think of them as sort of jumping back and forth in what we call the electron cloud. And sometimes this electron cloud is called a shell. And we'll talk about shells in physical science too, if any of you ever decide to take it. Now, here you can see everything is symmetric. And so the center of all the electron locations averages out to equal the center where the proton is. And so this guy has no net electrical forces because there's really no separation between the positive and negative charges on average. But sometimes atoms can become distorted. And so the proton gets shifted over a bit, but the center of the electron cloud is still here, and this creates what's called a dipole. Now, you don't actually need to know that word, but what you do need to know is that the atoms can kind of get smushed out, and that causes a separation of the charges inside the atom. And when atoms are distorted in this way, they're forming these little dipoles. We call this process charge polarization. So the charges are polarized when they're spread out like this. Here we can see sort of a familiar example of charge polarization. You probably experienced this at some point when you were a kid. If you ever rubbed a balloon across your hair and pressed it against the wall and let it go, you might have marveled at the fact that the balloon will stick to the wall and just be held up. And what's happening here is actually a two-step process. So the first step is you rub the balloon in your hair. You're actually transferring electrons from your hair onto the balloon, and so the balloon is made negatively charged. And when you press it up against the wall, the atoms in the wall get distorted. They become polarized. The electrons in the balloon push the electrons in the atoms away because like charges repel, and they attract the protons. They pull the nuclei closer, and so the atoms in the wall get smushed out and distorted, so the positive charges get pulled over close to the edge of the wall, and the negative charges get pushed away. Now, what also happens, we remember, these guys are attractive, and the electrons are repelling. The protons here are closer. Now remember Coulomb's law. The force equals to that constant times the two charges multiplied together divided by the distance. What that means is the further the distance, the weaker the force. Or conversely, the closer you are, the stronger the force. And so even though there are just as many electrons over here as there are protons, the protons are closer, and that means the force is stronger. So these protons are able to hold the balloon in place. Now, eventually what happens is the air molecules bumping into the balloon, they'll essentially knock some of these charges off the balloon, and so the balloon will become less and less charged over time, and eventually it'll just fall because there's not enough strength to hold it up. But by doing this, if you remember when you were a kid, it can actually hold there for quite a while. So it's kind of a neat demonstration of this polarization effect. Anyway, that's the first part of our lecture. We will continue in the next part very soon.